So we have a golfer who wishes to make a chip shot into a hole that's 50 meters away on flat level ground. So we need flat level ground. We will make flat level ground. There we go. And this guy is going to make a chip shot. And it's going to be shot at an angle of 45 degrees. So there's a shot at 45 degrees. So we know that the angle in here, okay, is 45 degrees. Okay, and this is going to projectile into a hole right here. Okay. Just make the projectile look a little better, and we've got our landing velocity. Okay, so the only thing we really know about this problem, in terms of anything, we don't know what the initial velocity is. In fact, that's what we're looking for. We don't know what this final velocity is. Okay. But maybe I do know some things in terms of x and y direction. For my x direction, all my x direction stuff, we're going to use red. So I know my range, or my displacement in the x direction. I know that equals 50 meters. And it appears that I don't really know anything else about the x direction. I don't know how much time this takes. I don't know the initial velocity in the x direction, the final velocity in the x direction. I don't know, I don't seem to know much of anything. Let's see what we do know in the y direction. Let's pick green for our y direction. So we do know that acceleration in the y direction is equal to, I use negative 9.81 meters per second squared. And I use that because I know down is what I call negative. So if I don't know anything else, I'm going to have to start picking this object apart. And I do know some things about this position right here, and we call that the peak position. We'll call that P. Okay? I do know that my velocity in the y direction at this spot is equal to 0. It has no up and down velocity. That's a spot where in the y direction it stops moving in the y direction. It only has horizontal motion. So let's take a moment to list down all the information we have in the x direction and all the information we have in the y direction. In the x direction, let's look at our given information. The initial velocity in the x, we don't know, but we do know that it's equivalent all around, so that's equal to the final velocity in the x direction. That's also equal to the velocity at P, the P position in the x direction. So they're all equal to it. So we got a constant velocity in the x direction. Our acceleration in the x direction, that's 0. Because we have a constant velocity. Our displacement in the x direction, that's equal to 50. We do know that that's basically one of our only given pieces of information, but it's 50 meters. And our time for the total x direction, for that total displacement of 50, then our total time is something we don't know. But we do know that time is equal to 2 times the time to peak. Okay, so let's also list what we have in our y direction. In the y direction, we have the following information. We don't know the initial velocity in the y direction. That's question mark. And let's, because we have some information at the peak, then let's analyze this at the peak position. So let's restate that y at the peak position. The initial in the y direction is question mark. The final in the y direction at the peak at this spot, that's equal to 0. My displacement in the y direction, we don't know. Acceleration in the y direction, that's equal to negative 9.81 meters per second squared. And my time at my peak, I don't know. But I do know that there's some relationship here between these two items. Okay, there's some kind of relationship here. And we've already shown that by saying total time is equal to 2 times the time to peak. So if I go about solving something in the x direction, if I look at my displacement in the x direction and I try to have a displacement equation, specifically because I have displacement, and I'd say, okay, displacement in the x direction is equal to initial velocity in the x direction times some amount of time plus 1/2 a t squared. And you could use either displacement equation, and you'll start to see this shake out as, well, eventually displacement is just going to be equal to whatever the velocity is in the x direction times your total time, This is going to go away and be 0, so this is your equation in the x direction. And if we plug in information for this, this is 50 for our displacement. We still don't know our velocity in the x direction. And the time is our total time. Okay, so we've got an equation here with two unknowns. So we're going to need a second equation. So this is our first equation. So maybe that's going to come through solving things in the y direction. And again, we're dealing with everything happening at the peak position, but maybe we have some information that can help lead us to a second equation that we can make equivalent to this equation and do simultaneous solving. So in our y direction, at the peak, we can say the v final in the y is equal to the initial velocity in the y plus acceleration times time. And the reason we'd use this equation is because we know our final velocity in the y, don't know the initial velocity in the y, we do know our acceleration, and we know we have a time relationship between the x because of this relationship. So final velocity in the y, that's 0, equals v v initial in the y direction plus negative 9.81 times, this is time to peak. Okay, we're dealing with that to peak, that's the time to peak. Okay, so now this is our second equation here, right? We have initial velocity in the y, we have a velocity in the x, which, you know, we could have just continued to say it's the initial velocity in the x, okay? And let's write that in, just because it doesn't matter. The final velocity in the x is the velocity in the x is the initial velocity in the x. All the velocities in the x direction are all equivalent. But we want to somehow relate these velocities. So we're going to call this initial velocity in the x. We probably could have done that throughout solving this problem. We could have done that in the same order. Anyway, what we have here is 1, 2, 3, 4 unknowns. And we only have 2 equations. So I can relate total time and get rid of the total time variable and put it in terms of time to peak, TP. And the way I would do that is substitute in 2 times time to peak. You're left with an equation that looks like this. So we're going to move this down here and say this is 50 equals initial velocity in the x direction times, this is going to be 2 times time peak. That's substituted in for total time. Okay? The reason I do that is because now I only have 1, 2, 3 unknown variables. So now I've got to somehow relate these two. And that's where trig is going to come in to play, and that's where our angle is going to come into play. Okay? I know the following 2 formulas in terms of the initial velocity and the launch angle. And those equations are as follows. I know that the velocity initial in the x direction is equal to my initial velocity vector times the cosine of my launching angle. Do I know my launching angle? Yes, it's 45. So this is the initial in the x direction. The x component is initial velocity times cosine of 45 degrees. And in the y direction, I know that my initial velocity in the y direction is equal to the initial velocity vector times the sine of the angle. Okay, this initial velocity vector, okay, times the sine of the angle for my y component. And we still don't know what that initial velocity vector is, but maybe you can start seeing where this is going to go. We do sine of 45. Let me just rewrite that in a similar fashion to what I wrote over here. So VI times the sine.
It does a certain thing.
I lost my place, but this finishes out to be sine of 45. So we have an equation for VIY, and we can take this and plug it in here, and we can take this and plug it in here. and let's see what that does for me. So if I copy this, put it down here, let's copy this. So instead of copying that up, just rewrite it down here. And we're going to take this information and plug it in for your Vx. And we're going to take this information plug it in for your VI y. And we'll see what happens. This will become 0 equals VI times sine of 45 degrees plus a negative 9.81 times time peak. This becomes 50 equal to VI cosine of 45 times 2 t. And then we can see that we have 1, 2 unknowns that are the same unknowns. We have 2 equations. We've effectively reduced down our unknowns, and we can solve. We can solve for your VI and plug it in over here, or you can solve for TP and plug it in over here. Whatever you choose to do is fine. But from here on out, you should be able to take this and solve for both the time to peak and also your initial velocity. And that would be your initial launching velocity. And I'll show that. So sine of 45 is 0.707. And that's going to be multiplied by VI minus 9.81 times TP. And we're going to solve this for TP. So we're going to isolate TP on this side and plug it in over here. So let's extend the page a little bit, and we can add 9.81 TP to both sides. And then we can say this is 9.81 times TP on one side of the equation equals 0.707 times VI on this side of the equation. And we can divide both sides by 9.81. That cancels out. You get time peak is going to be equal to 0.707 divided by 9.81 times VI. And this would be equal to 0.0721 times VI is equal to your time to peak. So I take that information and I plug it in for TP. So I'm going to take all of this stuff that's here, and I can plug that in for time to peak. And then this equation becomes 50 equals VI times cosine of 47 cosine of 45 is equal to 0.707 also. Times 2 times your time to peak. The time to peak is 0.0721 times initial velocity, close the parentheses outside, and calculate. So we've got 50 VI, let's multiply all these whole numbers. Okay, 0.707 times 2 times 0.0721, then that's equal to 0.10, round it to 2, times another initial velocity. So this VI times VI is equal to VI squared times 0.102, and that's equal to 50. If we divide both sides by 0.102, those cancel out. We're 490.2 equals VI squared, and we're not done yet because we got to take the square root of both sides, and we'll finally arrive at our initial velocity equal to 22, somewhere around 22.1 meters per second. And that is our final answer for the initial velocity that needs this ball, initial speed that this ball must have in order to reach